Welcome to episode 12 of CipherVibe's end-to-end cloud security architecture course. Hardware-level isolation adds protection for selected data while it is being processed in memory. It is useful for sensitive computation, but does not replace application security, identity, encryption, or operational discipline. We will connect its purpose, design boundaries, implementation path, failure modes, and evidence of effectiveness. Every cloud security layer relies on the ones around it. Confidential computing sits beneath workloads and data services, while relying on key management, attestation, image integrity, and lifecycle controls. Its value depends on a precise threat model and verifiable trust chain. Treat the architecture as a chain. A trusted identity requests an action, a policy makes a decision, a workload or data service enforces it, and telemetry records enough context to investigate later. The first building block is start with a threat model. Identify what data must remain protected during processing, which parties are trusted, and which infrastructure or operator threats the design addresses. Confidential computing can reduce some memory exposure risks, but it does not solve insecure code, compromised credentials, malicious input, or poor key governance. The second building block is use attestation before release. Remote attestation lets a relying service evaluate measurements or claims from a trusted execution environment before releasing sensitive material. Define accepted measurements, software versions, and policy ownership, then record attestation outcomes so changes do not silently weaken the trust decision. The third building block is minimize the trusted computing base. Keep enclave or confidential workload code small, use reproducible and signed artifacts, isolate sensitive operations, and govern updates carefully. Every library, configuration, debug feature, and management interface can expand the trusted computing base and complicate assurance. The fourth building block is plan lifecycle and operations. Design operational paths for upgrade, failure, scaling, debugging, key rotation, backup, and recovery without weakening the protection model. Capture health and attestation evidence while avoiding sensitive memory or secret leakage into diagnostic logs and support tooling. Use this reference pattern. Begin with an explicit policy that describes the permitted outcome. Enforce that policy at the closest reliable control point. Route decision and activity evidence to protected storage. Then give an accountable team a tested path to review exceptions, correct drift, and respond to violations. A practical design protects a well-defined computation, verifies the runtime through attestation, releases keys only after policy passes, and treats updates and recovery as part of the same trust chain. Implement this layer in a sequence that preserves evidence and limits blast radius. First, write the threat model and select the exact sensitive computation second. Choose a supported confidential computing deployment model third. Define attestation policy and key release ownership fourth. Build minimal signed workloads and disable unsafe debug paths fifth. Test update, failure, and recovery without bypassing protection. Prefer pilots with a named owner and rollback plan over an unmeasured organization-wide switch. The best rollout is one where a normal workflow succeeds, an unsafe path fails closed, and the team can explain the decision from logs rather than intuition. Security architecture fails most often through assumptions, not dramatic movie-style attacks. First, using enclaves without deciding what threat they address second, releasing keys based on ungoverned or stale measurements third, expanding the trusted computing base with unmanaged dependencies fourth, assuming confidential memory protects data after it leaves the workload. A configuration screen is not assurance. Collect evidence that the intended control applies to the correct scope and that violations become visible. First, record attestation success and denial evidence second, test a changed measurement and confirm key release fails close third, review workload image provenance and debug configuration fourth, exercise recovery, key rotation, and monitoring with safe test data test both normal activity and a safe negative case in an authorized environment. Record the expected decision, the evidence location, the owner who reviews exceptions, and the rollback method. Repeat after platform changes, new integrations, or major shifts in business use. For a practical exercise, outline a confidential analytics workload that processes synthetic regulated data and releases a decryption key only after attestation. Use synthetic information or an environment you own or are explicitly authorized to administer. Deliver a one-page diagram, a concise control statement, a list of expected audit events, and one test for an allowed path plus one test for a denied path. This artifact is more valuable than a screenshot because it explains the reasoning behind the configuration. Before scaling this layer, ask 5 review questions. Which assets, identities, or environments are in scope? Who owns the desired state and exception decisions? Which enforcement point can reliably apply the rule? Which records prove the decision and retain enough context for an investigation? And how can the organization revoke access, contain impact, or roll back safely when a control fails? Good architecture makes these answers explicit and testable. The key lesson is that hardware-level isolation becomes dependable only when design, policy, enforcement, evidence, and ownership move together. Document the decisions you make, remove permissions and exposure that do not support a real requirement, and rehearse the paths that matter before an incident forces the lesson. Continue through the next episode to connect this control layer to the rest of the CipherVibe cloud security architecture.